Hi, I'm trying to find the integral of this function secant theta tangent theta divided by 1 plus secant theta. And the key to being successful at taking integrals is to be aware of derivatives. So more than half the time when you take an integral, you're actually just thinking about the derivative of a function. And you're trying to see if the derivative of a function is somehow attached to the integral. And in class we talked about a few things that you could let u be. So u could be something like a base of something raised to a power. U could be the radicand inside a square root or a cube root. U could be a power if you have something like e raised to a power. U could be an angle, and u could be the denominator of something, a rational expression, and sometimes we let u be, what else, let's see, the argument. For instance, if you have ln of something, you let u be that something. And many times it is trial and error, but practice makes you better at taking these integrals. So let's see, do we have a base in this problem? No, nothing is being raised to a power. Is there a radicand? No, there's no square roots or cube roots. Do you see e raised to a power? No. Angles. Yeah, we have angles, but all the angles are theta. Secant of theta, tangent of theta, and again secant of theta. And we're never going to let u just be equal to theta, or let u just be equal to x. So not an angle. Denominator, well, I have a denominator 1 plus secant theta. And so I start thinking about the derivative. What is the derivative of secant theta? Well, if I choose u as secant theta, the derivative is secant tangent, and I see it exactly there. So then I could be tempted to say let u be secant theta, but if I do that, I will get nowhere with this problem, because what I should do instead is let u be equal to the entire denominator, 1 plus secant theta. That way when you take the derivative of 1 doesn't account for anything, it'd be 0, and you still get the benefit of the derivative of secant theta, which is secant theta, tangent theta, d theta, and that is exactly what we have in the numerator, and so we are ready to rewrite our integral. Now as the integral of secant theta, tangent theta, d theta, this whole expression is going to become du, and 1 plus secant theta is our substitution u, and this just becomes the integral of 1 over u du, which is the ln of the absolute value of u plus c, and that is the ln of whatever u was, which is 1 plus secant theta plus c. So again, don't forget the list of items that we could let u be equal to. And many times you just have to go down the list to see what the better substitution is. And also, don't be afraid to let u stand for an entire expression in the denominator. Here's a second example. And now I am divided between two things. Should I let u be equal to a power, or should I let u be equal to the denominator? And when you look at it, the funny thing is that the power is the square root of x. The denominator is also the square root of x. So it feels like there's no difference what you choose, but you should be thinking about it. Am I going to let u be the square root of x, which is the denominator, or am I going to let u be the square root of x, which is the power? Okay? And what you should do in this instance is you should let u be the power square root of x. So this here will become u, like there. And so now the derivative, well, I can rewrite this as x to the 1/2. And then du would be 1/2 x to the negative 1/2 dx. And if I rewrite that, du would be 1/2 square root of x when you bring the x down from the negative exponent. And so let me rewrite this integral. It is the same as saying the integral of e to the square root of x times 1/, the square root of x dx. And now you can see that this part is right there, but we are missing the 2. This is what some of you got wrong last time. You're supposed to get rid of the 2, and to get rid of this 2, you don't divide du by 2, you multiply both sides by 2, so that we have 2 times du is equal to 1/, the square root of x dx. Okay, so multiply both sides by 2. Again, many of you missed that little detail in one of the example. I think it was your last quiz problem assignment. So then, now I have the integral of e to the square root of x, and that was the u substitution. So e to the u, and then 1/, square root of x dx is now 2 du. 2 du. And we can take this integral. It's just e to the u again plus c. And now we can do back substitution and say this is 2e to the square root of x plus c. And it's always a good idea if you have some extra seconds to double check and just say, hey, let me take the derivative of this. What would it be? 2 times e to a power. The derivative of 2 times e to a power would be 2 times e to the same power times the derivative of the power, which is 1/2 x to the negative 1/2. And then if you rewrite that, it would be, well, the 2's cancel out, so it would just be e square root of x over square root of x. And that's exactly what the integrand was. And that's how we know we have the right answer. Here's my last example. I'm trying to figure out the integral from negative 1 to 1 of f of x dx. Now, remember, the integral is the area between the curve and the x-axis. So here I have this semicircle, and the problem is that the figure that it creates between the curve and the x-axis is not a geometric shape. You can see here that this area is actually more of a wedge shape, but it's not really a triangle, it's not really a trapezoid. So how do I figure out that area using geometric formulas? Well, what's going to help us here is to think about big minus small. So what I'm going to do is see that there is a rectangle here. So I'm going to take the whole area of the rectangle, and then I'm going to subtract the area of the semicircle, and when I do that, the area that's left is the area defined by the integral. See that? So it's going to be area of a rectangle minus area of a semicircle. So that would be length times width minus pi radius squared divided by 2. And what do we get from there? I didn't give you a height, and I'm running out of time, but it's basically get the area of the rectangle, take away the area of the semicircle, make sure you divide pi r squared by 2 to get the semicircle, and the remaining area is the area given by the integral. So sometimes you have to think about it this way: the big picture minus the small picture, and sometimes you have to think of pictures that are not obviously given. Like here I had to imagine a rectangle being part of the picture and then taking away the semicircle. Okay? Bye.